Okay, let's take a look at example of Unit B2, page 2. Okay, this is the example program comparing incompressible and isothermal pressure variation within atmosphere. So let's take a look. The Empire State Building in New York City, one of the tallest buildings in the world, rises to a height of approximately 1,250 feet. Let's estimate the ratio of the pressure at the top of the building to the pressure at its base, assuming the air to be at a common temperature of 59 degrees F. That means temperature doesn't change, isothermal condition. Let's compare this result with that obtained by assuming the air to be incompressible with a constant specific weight gamma 0.0765 pounds per cubic foot at 14.7 psi, absolute value for air. Okay, let's take a look. So, we are going to analyze this problem in two different ways. Let's just start with the figure here. So this is Empire State Building in New York City. The height is 1,250 feet. Okay. Let's see, this is a location 2, right here on top of the building. Root of the building, location 1. So at the location 2, pressure is P2. Location 1, pressure is P1. So we are going to determine the ratio between pressure P2 and P1 under two assumptions. A, let's assume isothermal. Means temperature 1 is equal to temperature 2 is equal to 59 degrees F isothermal. Temperature doesn't change between location 1 and 2. If so, what is the pressure ratio? Okay. We are going to obviously use this equation, isothermal pressure variation equation we derived. Okay. So this is the equation we derived in the class, isothermal variation of pressure within atmosphere. So let's just find out pressure ratio P2 over P1. This is essentially exponential of that. So let's just plug in. Gravity, let's assume 32.2 feet per second squared. This is a standard sea level gravity. Z2 minus Z1 is 1,250 feet. Altitude difference between 2 and 1. Gas constant, let's assume standard air, 1716 foot-pound Slag Rankine. Temperature is common 59 degrees F, but be careful. You can't use degrees F, you have to add 460 to make it Rankine. Okay? So if you punch the number in your calculator, this is going to give you 0.956. So this is a pressure ratio between top of the building and bottom of the building, assuming if the temperature doesn't change but stays constant with this value, isothermal condition. Chances are it may not be true. If you go on top of the building, it's going to be probably lower temperature here. Okay, so make sure this is based on assumption. You're going to repeat the same calculation based on a different assumption. Suppose if air does not change its specific weight, which is, we are going to assume air as incompressible fluid. Incompressible means density is constant. And also, gravity is constant. Gamma is rho g. So if density is constant, gravity is constant, this is also constant. Which in this case, let's assume constant value of 0.0765 pounds per cubic foot. Okay. If so, what is the pressure difference? Now in this case, obviously, we are going to treat this whole thing as a big hunk of rake somewhere. Right here is a pressure P2. Pressure goes up and up and up and up and reaches pressure P1. What is the difference? Gamma H. P equals to gamma H. Okay, because gamma is constant. So from that perspective, you can say P1 is P2 plus gamma H. Right here, pressure is P2. If you go deeper and deeper and deeper and deeper and deeper, you become pressure P1. Which one is higher pressure? P1 is higher pressure than P2. This is the difference. Okay. So from here, you can say P2 is equal to P1 minus gamma times Z2 minus Z1. You can divide both sides by P1, saying P2 over P1 is equal to 1 minus gamma times Z2 minus Z1 divided by P1, which is equal to 1 minus gamma is given 0.0765 pounds per cubic foot. This is 1,250 feet. P1 is given 14.7 pounds per inch square. I don't like that unit, so I'm going to convert it to pound per feet square. 12 inch over 1 foot square. Okay, so make sure you use foot, not inches. You're going to immediately convert inch into foot. Then you're going to have 0.955. So what is important from this example problem? Obviously for height of 1,250 feet, those two are about the same thing. It doesn't make much difference. Let's go take a look at this page here. So you're looking at the altitude of 1,250 feet. Those two lines correspond to the analysis based on constant temperature isothermal versus constant specific weight, which is incompressible assumption. Okay. At the 1,250 feet level, it's about the same thing, but it is going to depart into two different streams. So let's say 5,000 feet altitude, you're going to have this much difference. Okay. So obviously those two are based on assumptions, and assumptions usually break down as you go for higher and higher altitude. All right. So I guess the next step we are going to see here is what is the most accurate model to predict pressure within atmosphere. It's called U.S. Standard Atmospheric Model. This is very much different from isothermal assumption or incompressible and gravity constant assumption. Okay. So we are going to run this model, and typically in L1, L2, we are going to use this model to figure out what is the pressure for a given altitude. Okay, that's it.